Hi, I'm Reece Coleman, Waterways and Wetlands Research Manager in the Applied Research team at Melbourne Water. Thanks for joining us for another edition of Melbourne Streams, where we're showcasing research coming from the Waterways and Wetlands Research Program. In this first series, we've released a talk a day based on topics voted on by the Waterways and Land crews. Today's talk is a dynamic duo, Daniel Zhu, PhD student, and Dr. Matthew Burns of the University of Melbourne and the Melbourne Waterway Research to Practice Partnership with Melbourne Water. Both Daniel and Matt are hydrologists with an interest in understanding the impacts of urban stormwater on stream health, including catchment hydrology and modelling the performance of stormwater control measures and eco-hydrology. The title of their talk today is Enhancing the Environmental Benefits of Rainwater Tanks Using Real-Time Control. Daniel kicks off talking about the impacts of urban stormwater on stream flows and flooding. He then talks about how smart tanks, or rainwater tanks where we actively release water from them, could be used to help with some of the challenges of urban stormwater. This includes linking the tanks to the Bureau of Meteorology forecasts so that we can optimise stormwater capture. Matt then goes on to talk about an exciting project, the Monbolt Creek project, where we want to scale up this sort of technology, where we have rainwater tanks linked to urban storages, and we're actively releasing flows for the health of Monbolt Creek. This is consistent with a healthy waterway strategy target for Monbolt Creek and an integrated water management strategy target for the Dandenong Creek catchment. If you have any technical questions about this talk, then feel free to contact Matt or Dan directly. Their contact details are in the presentation. If you have broader questions about the Melbourne Waterway Research to Practice Partnership or Waterways and Wetlands Research Program, then feel free to contact myself or Slobodanka Stojkovic, who's also in the Waterways and Wetlands Research team. Of course, now you can also go on the intranet and search for the Research Hub and get access to the various projects, reports, papers, presentations, and so on that we've delivered over the past 10 years or more. I should also add that this research is in collaboration with South East Water and Yarra Ranges Council. And within Melbourne Water, Andrew Grant and Sarah Watkins have played a really important role in the Monbolt Creek project. I really hope you enjoyed Daniel and Matt's talk today, and we look forward to providing more talks in the days to come. Thanks.
Hi everyone, my name is Daniel, and I'll be presenting our latest research on smart rainwater tanks with my colleague Dr. Matthew Burns. My presentation today is called Enhancing the Environmental Benefits of Rainwater Tanks Using Real-Time Control Technology. I know more and more people are talking about how we can make our water assets smarter. Today, I'll be sharing some of the latest research at the Waterway Ecosystem Research Group. Apologize in advance if we slow down a little bit. Today, I'll presenting four main components. I'll start talking about some background of the stormwater issues. Then I'll introduce the general concept of how these smart rainwater tanks looks like and what are the research we've been doing at work around this topic. Then I'll presenting some of the latest research, how we enhancing the smartness of these systems by using 7-day rainfall forecasts. At the very end, Dr. Matt Burns will join me to presenting how this technology can be upscaled and applied in the Monbolt Creek catchment. Just to start with some storm issues, in the natural environment on the left-hand side, the rainfall are largely infiltrated through the pervious surface, such as grassland, and form the environmental baseflow in the downstream. Only small amount of water remain as the surface runoff. However, in contrast, in the urban environment on the right, this natural water cycle is heavily damaged and changed. The impervious surface we build, such as roofs and roads, stop that infiltration process. Most of the water becoming the surface runoff, and this not only cause serious urban flooding issues, but also deplete the environmental baseflow and damage the natural habitats. One solution to cope with these changes is using stormwater control measures, such as rainwater tanks. Rainwater tanks have multiple objectives. Conventionally, they are a source of water, collecting the roof runoff and supply the water needs in the house. Because they reduce the amount of roof runoff, they also have simultaneous benefits of mitigating the flooding risk in our urban environment. By installing a small trickle release to these tanks, making a passive release systems, they can also restore the base flow for our streams. However, we increasingly seeing, applying these real-time control or smart technology in our water asset to make them smarter. So one overarching question for us is, can we enhance these benefits by making the static rainwater harvesting systems more smarter using real-time control technology, and enhancing all the benefits, especially the base flow? So we design a smart control, and how does this system work, you may ask? So first of all, this system normally harvests the rainfall forecast data from the local Bureau of Meteorology. By receiving this forecast, the system would review the tank levels and ask whether this forecast rainfall would fit in those empty space. Then the system would start calculating whether you need to empty additional room to contain those forecast inflow. So after making those calculations, system would then perform a quick discharge, what we call pre-storm release, to empty the tank on a daily basis. And this type of discharge happening quickly with the sole purpose to reduce the flooding risk. We also design another type of automatic discharge, what we call the base flow release. In contrast, this release performs slowly and more persistently with the aim to restore the base flow in our streams. So we want to figure out how this system performs. So we built up a model to testing the effectiveness of these systems. So we model a range of tanks and roof sizes using the smart control that we design. We assess the performance across water supply, flood mitigation, and base flow restorations. And in that modeling studies, we found using these smart real-time control can enhancing the environment flow performance of the rainwater tanks, as well as increasing the stormwater retention performance, but only cause a little detriment to the water supply. And this work has been published in 2018 on the Water Journal. After that, we then ask ourselves, all right, so you've already proved this concept in the modeling world, how this performance would look like in the real world. So we really want to figure out a proof of concept in empirical studies. So we partnered with Southeast Water and set up a trial site in one of the residential house. We install all the real-time control equipment and monitoring in order to get a full understanding of how these tanks working. So we have real-time monitoring of tank level, inflow, overflow, tank discharge, and rainfall as well. And it's quite challenging to monitoring, the tank inflow and overflow. So we also, in that study, we also designed some novel structures to monitoring the tank water flows. And one of the conclusions we have in that empirical study is that the model tank operation can be achieved in the real world operation. Here's a video that we took when we happened to on site to testing the valve discharge, just to give you a bit of understanding how this discharge works. So at a specific time of the day, when the system determines I need to discharge some water for either for stream or flood mitigation purposes, the valve would opening and start to discharge some water at the downstream. So, so here we are actually recording how much water come out at each operation. After that, we also think so we've already known that using this technology can really give the benefits to the rainwater harvesting system in the multiple objectives. How can we make this control even more smarter after that? So we are investigating, can we using a more long-term rainfall forecast to make the effectiveness control more higher? So in this study, we're also asking, whether can we advance this smart control using a longer period rainfall forecast. So we adopt the 7-day rainfall forecast from Australian Digital Forecast Database, and we developed a model which allows you to generate a discharging plan. And this model is run continuously to optimize on a rolling forecast. The model would then demonstrate how effective of the different strategy generated for multi-objective outcome. So from the chart over here, you can see you're receiving the forecast at this blue window here. Based on the algorithm we designed, it's generating 4 different discharging plan with different design purposes to perform a discharge in the next 7 days. The different preference of the objective, including the flood mitigation. So some of the strategy have really high priority in mitigating the flooding risk, and also there's other strategy prefer to release the water over a longer period, but with a lower rate in order to protect the downstream habitat. The generated plan is also modeled by the tank model in the long term in order to assess its performance over the long period. And how this discharge would look like compared with the other smart control. All right, so this is the modeling. This modeling is done in a 60.5 time frame with using one specific event to demonstrate how this system performed in a 20-year event on 27 January 2016. The top figure is the rainfall in this period, and the bottom figure shows the outflow in this period. The green line here is our real-time control technology using the 7-day forecast, while the red line demonstrates a conventional rainwater tanks. What it does with real-time control is the system receiving the forecast on 23rd of January and decide to release some water 7 days ahead of the rainfall actually occurred, which is on 27th January. The discharge is finished at 24th and they go back to a low discharging for the environment-based flow. However, this discharge is then adjusted due to the forecast error when the date is closed in order to mitigate the tank overflow. So on the 27th January, the real-time control tanks don't have any overflow, successfully contain all the runoff. However, in contrast, the conventional tanks just overflow, just spill all those inflows during the rainfall. Also, because of this rolling window and you are consistently predicting for the future, the water in the 20-year events is also, the overflow in that 20-year events is also being mitigated after the tank is mitigating all the flooding risk. They go back to the duty to restore the environment flows when there's no risk of flooding. What we found in this study is using 7-day forecast further enhance the performance of the smart tanks. we're also looking at what's the impact of the smart control over a long-term hydrology. So here is the flow duration curves of all the scenarios we models. We also compare with the conventional system, which is shown in the red line. We also compare with a reference stream flow, which is the flow gauges, one of the Melbourne Water flow gauges as the Monbulk, as a comparison group. So the flow duration curve is a cumulative frequency curve that shows the percent of time specified discharge were equaled or exceeded during a given period. Here we're really just trying to reflect how our control discharge is affect our flow regime and compare to the others. All you want to look at with this chart is the trend of it. So if we're looking at the bottom left one, you can see that by equip the rainwater tanks with smart control, the peak flow is largely decreased. And although it still has distance with the natural flow, stream flow, you can mitigate a lot of peak flow in the urban environment. And look at the right bottom chart, you can see the real-time control can also successfully restore the base flow, deliver a base flow that's higher than your reference stream. What is really interesting over here is these two green line over there, they actually mimic the trend of the blue line, which is the natural stream flow. And we found that, you know, by using this technology and all the strategies that we designed, this technology can potentially restore the full regime of the natural flows, which demonstrates its ability to manage stormwater in a more environmental way in a range of contexts. And this research has been recently published on one of the top international peer-reviewed journal. All right, next, Dr. Matt Burns will join me to presenting how this technology can be upscaled in the Monbulk catchment. And to you, Matt.
Thanks, Daniel. That's a really great job. So Daniel's done some really great work, both empirically and in a modeling sense, showing that if we put real-time control technology on rainwater tanks, that they can obviously provide a water supply benefit, provide a flood benefit, but also provide an environmental flow benefit. And that's a really innovative part of Daniel's work and use of this technology. So we've been working with Melbourne Water to deploy real-time control technology throughout the Monbulk Creek catchment. And so the Monbulk Creek catchment, it's a fairly peri-urban catchment. For example, the township of Belgrave is in the catchment. A couple of interesting features about it include two big public storages. So there's Belgrave Lake there in the middle, which is it used to be a water supply reservoir, and also Birdsland Reserve, which is primarily a retarding basin. So there's these two big storages, and there's also this sort of mix of private and public properties, and so but there's this huge potential to deploy real-time control technology at the private scale, so individual households, at larger scales, so businesses, schools, other council buildings, and also deploy this technology on these two big public storages. So some of you are probably thinking, what's this sort of great interest in Monbulk Creek? So if you go to the next slide, Daniel. One of the key drivers of why Monbulk is that there is a platypus population that lives within Womboll Creek. It's one of the last remnant platypus populations of the Dandenong system, I believe. And this particular platypus population is at risk of extinction because of stormwater runoff. So all the stormwater that's generated from Womboll Creek catchment, but it's also at risk because of climate change. So climate change is predicted to reduce rainfall, which will reduce stream flow, and so there's a potential that particularly during dry weather periods, so particularly during sort of these warmer summer and autumn months, that with the change in climate, there's going to be less water in the stream. That means less physical habitat, and that could in turn reduce food supply to the platypus and then start stressing them. And so there's this really exciting potential to put these smart tanks all through Womboll Creek, so houses, schools, council buildings, and these two big storages, and to develop and to use the technology in a really sophisticated way to ensure that we can provide the right environmental water for the platypus at the right time. And so this is some work that a colleague Reece Coleman was involved with in showing the sort of flow regime that the platypus populations require. And what it means is, for example, this work identified that the autumn periods, particularly higher flows in autumn, are particularly important from a breeding perspective. So you can imagine that with these tanks, we can control the smart network to build up water in these storages and then release it in this particularly important autumn period when the platypus need it. So again, following on from Daniel's work in using technology to provide an environmental flow that matches the requirement of the ecosystem, which is really exciting and innovative. The next slide. And so this just reinforces some work that we've done with Melbourne Water, showing that that this concept is certainly possible from a hydrologic and a hydraulic sense. And this is some music modeling, which is music is a hydrologic model. And what it shows is that it's really important for this to work in Womboll Creek, but also in other places, is that we really need a cooperation with the smart tanks at the household scale, working cooperatively with these larger storages. And so we have sort of thought that with this project, concepts like an individual household having a rainwater tank with real-time control. It's a really dry period. Stream flow is getting low. Physical habitat for the platypus are getting low, but they've got water in their tank. And potentially concepts like they could have a smart app. They get an alert saying, "Hey, the platypus need water. Would you be prepared to release some of your water from the tank, release it downstream, so that water can be potentially stored in some of these big storages and then released downstream, or potentially released directly to the waterway." So this concept not only has environmental benefits, but there's also a social dimension to it. So whether people for the first time being able to interactively provide environmental water at the allotment scale to the receiving water. There's also issues about the community interacting with this novel technology. So, do you think people would be comfortable having their tanks monitored, maybe even controlled remotely by Southeast Water or Melbourne Water, things like that? There's also economic questions as well. So maybe if a resident has a tank full of water, it's dry, and the receiving water would really like some, could a resident be financially rewarded by releasing some of that water? So this kind of public-private interactions with water, some really interesting questions there, and opens up potentially whole water markets, issues around community perceptions, those sort of things. So next slide there. And so I guess the current sort of status of this project is that the Melbourne Water are, and in conjunction with Yarra Ranges Council, the local municipality, and Southeast Water, the water retailer, are actively working on the business case for this project, and we're actively in the process now of working out exactly how we could retrofit Belgrave Lake with the smart technology, so we can control water level and then being able to release water when we need to, and the same for the retarding basin much further downstream. So this project is it's not a pipe dream. We're really sort of in the process of doing some functional design, and potentially, hopefully, in the next couple of years, we can start deploying some of these smart tanks out in the community. And it's particularly important to provide this proof of concept to hopefully roll out potentially smart tanks in other places. And Daniel's already spoken about that the tanks in the case of Monbulk Creek, one of the primary interests is in environmental flows for the platypus. But you can imagine that if you're somewhere like Fisherman's Bend, where flooding is a really important issue, that these tanks can provide really important benefits over conventional tanks in terms of flood management. So this proof of concept here proves successful, that we can start thinking about rolling out this technology in other spots, areas where drivers could be potentially different. So next slide. So that's all we have for you today. So thanks very much for the opportunity to give this presentation. I think it's a really great idea and initiative, from Melbourne Water, and it's a real privilege to be able to sort of communicate our research findings in this way, and so if you so Daniel's doing most of the grunt work on this real-time control. So if you've got any detailed questions sort of on the technology and on the tanks and on the modelling, you can contact Daniel there. And if you wanted to know a bit more about the Monbulk Creek project, feel free to contact myself. Or the people within Melbourne Water who are sort of actively involved, are people like Reece Coleman, Sarah Watkins, Andrew Grant, and of course we should probably acknowledge our partners, Southeast Water. So we're really working closely with Southeast Water, David Bergman there. So thanks a lot.
Thank you very much. Thanks for listening.